This program is brought to you by Stanford University.
We're discussing, just to fill in a point, which is an interesting point, the behavior of a light ray either in a gravitational field or in an accelerating elevator, not when the light ray is traveling across the elevator, but when the light ray is traveling vertical in the elevator. How do we understand, or what shall we deduce from Einstein's principle of equivalence? What should we deduce about a light ray which is beamed vertically upward, for example, and which is then detected up on the roof of the building somewheres? Right? Does anything interesting happen to that light? Now, of course, if light was just an ordinary particle, a bullet shot upward, you know what the effect of gravity on the bullet is. It decelerates the bullet. Bullet going upward, gravity pulling it downward, slows the motion, and effectively removes kinetic energy from the bullet. So the person on the ceiling sees a slower bullet than the bullet that we fired upward. Things are a little more involved when we take into account relativity, and in particular, when we take into account the relativity which has to do with things moving very close to the speed of light. No, we're talking now about light, things moving with the speed of light. Everybody sees the same speed of light, but something happens to a light beam that's fired upward. Namely, its color changes, or its frequency changes. And the effect is very easy to understand in the elevator. Not so easy to understand if you're thinking about gravity and you're thinking about, God knows, what is the effect of gravity on a vertical light beam? Don't ask that question, says Einstein. Ask, what's the effect of a light beam, let's say shot vertically upward from the floor when it's detected at the ceiling, or vice versa? I think I'll go the other way. Let's take the light beam shot downward from the roof of the elevator. And let's suppose that it has a certain frequency. Right? What happens by the time the light ray hits the bottom? By the time the light ray hits the bottom, in fact, let's imagine starting with the elevator at rest. It doesn't matter whether the elevator is at rest, but let's imagine starting at this time when the elevator is at rest with respect to us sitting here. Right? By the time the light ray gets down here, the elevator is now moving upward. But it's also got it isn't just displaced upward, it's moving upward with a velocity. In other words, what's seen down here is exactly what would be seen if a light ray was sent downward, but then intercepted by something with a vertical component of velocity. Well, you know what happens to a light beam when it's intercepted by something moving relative to the source. It's Doppler shifted. Just good old Doppler shift. So you can estimate pretty accurately, rather accurately, yes?
But wouldn't those Doppler shifts cancel?
No.
Because the source is moving?
No. When the beam was fired, the source was at rest. But the elevator is accelerating upward. So by the time the beam gets here, the elevator is moving upward. Right. Oh, constant velocity, they cancel. That's exactly right. Absolutely right. With constant velocity, the two Doppler shifts, the Doppler shift would cancel. Right. It's the accelerated effect which makes the detector be moving faster upward than the emitter. So it's a little exercise. You can do the exercise. Just say, now, there's a bit of an approximation here because you really should use the full general relativity or the full, at least special relativity in doing this. But you can get very close to the right answer just by saying, how long does it take the light ray to go from here to here? Well, it moves with the speed of light. The height of the elevator is h, let's call it. And you know as well as I do how to compute the amount of time that it takes for the light beam to reach the bottom. But then you can estimate, if you know how much time and it's been accelerating with a uniform acceleration, you can compute the upward velocity when the light beam hits the floor, and then just apply the standard Doppler shift formula. Go look it up on the internet, Doppler shift formula, and you can detect and you can determine the change in frequency during the fall of the light ray down to the floor. That's exactly the same effect that happens to a light ray near the surface of the Earth when it's fired downward. This has been tested in a big high tower, laser beam downward, detector, laser beam at the roof, downward, detector at the bottom. The color of the light ray is a little bit bluer than it would have been if it would have been detected up at the top of its arc. Okay? Precisely the same effect, well, precisely the opposite effect, of course, would happen if you fired the light beam from the floor and detected it at the ceiling. Then you would see a bit of redshift, exactly the opposite thing. And in fact, this is, of course, true when a light beam departs from the surface of the sun or anything like that. It's detected a little bit redshifted far away. So, for example, the spectral lines of various atomic transitions and things like that, when they would be measured on the Earth by a telescope, would be slightly shifted from the values you would expect because they were shifted by exactly this effect. It's a small effect for the sun. All right, so I just thought I would explain that phenomenon.
Wouldn't it be a large effect for a very large star?
It is a large effect. The relevant issue actually is the escape velocity. So if it's a large star, but it's spread out all over the place over a very, very large diameter, then the effect is not so big. If it's squashed, then the effect is big. And in fact, the effect is enormous from the surface of a black hole. From the surface of a black hole, the effect is huge. You know, the bluest light would appear, if emitted somewhere near the surface of a black hole, would appear deeply infrared by the time it got out. Okay, but that's another story that we'll come to. But generally speaking, I think the answer would be yes, it would be a bigger effect for a large star.
Yes, that bag is blocking.
Oh, excuse me. Very good.
Thank you very much.
You're welcome.
Isn't that light isn't going to bend around the bag?
That's right. Remind me the bag is here. Oh, Rick, will you remind me the bag is here? There's something in it for you. Here, I'll give it to you now. This is for the nice dinner that you served me, just in case you didn't bring me. I knew you wouldn't bring me a cookie, so. No. There's something. That was just in case my friend didn't bring me a cookie today. Yes?
So the light shift, the red, blue, doesn't that go against the equivalence principle? Because if you're...
It is the equivalence principle. It says gravity is equivalent to a field of acceleration.
Oh, okay. No, I think about the idea that in an accelerated frame of reference, if everything's moving with you, you wouldn't know that you're really...
No, that's not true. If you're in an accelerated frame of reference, you can tell either that you're accelerated or that you're in a gravitational field. You can tell that you're not in free fall. In free fall, if the elevator was freely falling, okay, so here's another issue. If the elevator is freely falling, let's suppose the elevator is freely falling in a gravitational field, and we do the same experiment, we shoot the light ray down. Now we are in a real gravitational field. The effect of the real gravitational field is to redden the light. But the acceleration of the elevator gives rise to a little bit of Doppler shift as it's moving down. And they exactly cancel each other, so that in free fall, the elevator experiment would not detect the shift of light. That's another example of the equivalence principle, that gravity can be canceled, so to speak, by a field of acceleration. Yeah. Up to a point that will...
Well, when the light was emitted, it's moving slower than when it's detected.
No, it's moving with the speed of light.
Yeah, but what I'm saying is that the floor is moving faster later on
Yep.
than when the light was emitted,
Yes.
so it'd still be stretched. It would be redshifted.
It's written
in free fall.
No, but that's canceled by the genuine blue shift due to the genuine gravitational field here.
Yeah, but it was blue shifted by a different amount than it was
No,
redshifted.
it's exactly. No, the blue shift, the shift in the freely falling elevator, there is no shift. They cancel.
But it's accelerating. It's
Yes.
not in constant velocity.
It's freely falling. It's freely falling, okay? It is accelerated. It's accelerated just like a real elevator would accelerate. It's accelerating downward. Two things are going on. One is the light beam as seen from the outside, as seen from outside the elevator, if the detector was standing still. If the detector was standing still, the light beam would be blue shifted. But now, because by the time the light ray gets there, the elevator bottom is moving downward, there is a canceling effect of a Doppler shift. Now, to prove that those cancel each other, you have to do a little calculation.
Well, I agree that there's going to be the cancellation effect, but there will be a slight difference because of the difference in the velocity at the time of detection and the time of the emission.
But that can't be, because if that were so, Einstein's equivalence principle would simply be wrong. What Einstein's equivalence principle says is that you get a complete cancellation, apart from tidal forces, apart from the fact that gravity varies in strength over the size of the elevator. Apart from that fact, it says that a freely falling elevator in a gravitational field is exactly the same as an elevator in free space, not accelerated with no gravitational field. All right, so I invite you to make a little calculation. It's just a little bit of application of Doppler shift. The formula for Doppler shift is easy. And I'm not going to do it on the blackboard now. And of course, if you really want to do it exactly, you have to do it with a special theory of relativity. You can't do it with just, it's true that if you do it just using non-relativistic formulas, you're going to get a little bit of shift, which is going to be second order in velocity divided by the speed of light. Using special relativity, you'll find that they exactly cancel. Okay, that's important. That's an important fact. Okay, let me just remind you, in reference to this again, that an accelerated reference frame can be thought of one in which the coordinate chart, let's think of a coordinate chart, coordinates, distance, we imagined the acceleration going off to the right. We imagined our elevator moving off to the right with some acceleration. And then I explained that the coordinate frame within the elevator, the meter sticks, let's see if we have another pen here. The meter sticks, which are standing at rest in the elevator, in the accelerated elevator, when viewed from the rest frame, of course, have a curved trajectory. That curved trajectory is the consequence of the acceleration. In fact, if we imagined that the elevator was accelerating forever, accelerating to the right forever, what that really means is that it came in from the left, it decelerated, and then when it went off to the right, uniform acceleration. That means long in the past it was coming in, it slowed down, and it accelerated off to the right. Then the trajectories of the endpoints of the meter stick would be parabolas. It would look something like that. The main lesson here is, oh, and of course, the rest frame, the meter sticks just stay at rest. Whoops, I didn't draw that very well, but you get the point. The interesting thing is the correspondence between gravity and the use of a curved coordinate system. We start perhaps in absolutely free space, and we use an inertial reference frame. And an inertial reference frame is just a frame at rest in which the meter sticks are standing still. In other words, it's the frame defined by these vertical y-axes or time axes, so to speak. But then we look at it from within the elevator, and from within the elevator, the trajectories, or from outside, excuse me, from outside the elevator, the meter sticks of the elevator are curved trajectories. And so we, outside the elevator, will blame the peculiar things that the person inside the elevator sees. What are those peculiar things called? Gravity. The peculiar phenomena of gravity, we will blame it on the use of these curved coordinates. We will say, sure, if we describe nature in terms of curved coordinates, we're going to see some funny things. The lesson is that you can remove the effects of gravity by going from one coordinate system to another, but to do so, you have to introduce various kinds of curvature into the coordinates. The curvature is just another way of speaking about acceleration. So, does the elevator have gravity in it, or doesn't the elevator have gravity in it? One analysis says it has gravity in it. The other analysis from another coordinate frame removes the gravity and blames it on acceleration. Now, what about real gravity due to a planet or a star or something like that? That's more complicated, as I mentioned last time or time before that. You could try to remove the effects of gravity by going to a freely falling vertical elevator. And indeed, that would remove most of the effects of the gravity of the Earth, for example, in a freely falling elevator. But there would be some leftover little bits, the leftover little bits of effect. And those leftover little bits would be the tidal forces, which are due to the fact that there's a variation in the strength of gravity, that gravity is stronger near the bottom than it is near the top. And in fact, if you looked at the overall situation where you might introduce a lot of elevators, there's obviously no way that any single choice of accelerated reference frame can remove the whole effect of gravity. The whole effect of gravity, at best, you could remove it within a small volume over which gravity doesn't change very much, over a relatively short time, which it doesn't change very much. That you can do. You can remove the effects of gravity in a freely falling elevator for a short time and a short distance. But you can't remove it globally. There's an obstruction. The obstruction is the non-uniformity of the gravitational field, which is caused by the mass. So mass presents an obstruction to getting rid of gravitational field by coordinate transformation. Yeah?
When you use Rindler coordinates, are you ignoring the tidal forces?
No. Well, first of all, I'm not using Rindler coordinates because I'm not doing special relativity. We're doing no. Okay, I know what you're asking, and it's more than I want to answer right now. Let's not get into Rindler. Yeah. Okay. We're still in the approximation where we're not really thinking about relativity. We're just thinking more or less Newtonian plus equivalence principle. All right. So you can't really remove a gravitational field by choosing accelerated coordinate systems. Tidal forces can't be removed. The fact that you have to accelerate in different directions at different places doesn't really make sense. As I said, there is an obstruction to getting rid of the gravitational field by coordinate transformation. That obstruction is closely related to the obstruction in removing the curvature of a curved space. And that's what I want to come to now. I want to come to the differential geometry and the mathematics of curved spaces. That's going to take us some time. We're not going to be able to do it all in one lecture. I'm not sure how many lectures. The basic tool is really no more complicated than the calculus, multivariable calculus. I have to assume that you're familiar with some multivariable calculus. I'm not going to teach it here, But really just partial derivatives and a little bit more than that is really all we need to get a start on the basic ideas of what curved space is, a curved space in space-time. We're not going to start with space-time, we're just going to think about space. And later on, we'll generalize things to space-time. All right, but before we start, just a very, very quick review of one or two very small things about multivariable calculus. We'll use them over and over again. Supposing we have some space, which we can draw as two-dimensional. We can put some coordinates on it. All right. We can put some coordinates on it. In this case, it's just a two-dimensional space, the space of the blackboard. There could be coordinates coming out. It could be any dimensional. And it's described by some coordinates. Let's call them x. If I really were just doing two variables, I might just talk about x and y. But I want to be more general. And so what I'll talk about is x1, x2, x3, as many as I need to describe the space. And how many do I need? I need as many as there are dimensions of space. So let's call the dimension of space d. This will go up to xd. That's how many coordinates. The horizontal one could be x1, the vertical one could be x2, the one sticking out of the blackboard that you can't see would be x3, and so forth. All right, now suppose we had some function that was a function of the x's. You can think of it as a field, if you like, something which just varies from place to place. Let's call it phi of x. X now stands for the collection, x1 through xd. I won't bother writing that it's a function of x1, x2, x3, just a function of x, and I'm calling it phi for, I don't know why I'm calling it phi. Now, let's consider the change in phi, the change in the value of phi, when you move a small distance. And let's characterize that distance, a small infinitesimal distance. Infinitesimal just means really small. Let's characterize that displacement, that infinite displacement, by a differential dx. This stands for a small displacement. This really means dx1, dx2. All right, so here would be dx1, here would be dx2, and if this vector pointed out into the x3 direction, there would be a dx3. So just like x stands for this collection of things, dx stands for small displacement of all the coordinates. Then how much does phi change in going from this point to that point? What's the change in phi? The change in phi we call d phi. The small change in phi, it's obviously related to the partial derivatives of phi with respect to the coordinates. I'm going to write the answer. It's just given by the small change in phi if you moved purely in the x1 direction times the small change in dx1 plus d phi by dx2, the small change in phi if you moved purely in the second direction. First term is the change in phi if you move this way. Second term is the change in phi moving that way, times dx2 plus dot, 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 as many terms as there are until you get up to the dth term. Right. This is, I don't even know what rule that's called. Has that got a name? I don't know what it's called. I don't know if it has a name or not.
Yeah, if you divide by dt over there, you get a dx dt, you know, so basically it's the chain rule.
Well, it's part of the chain rule, yeah. Yeah, it is connected to the chain rule, yeah. All right, now we're going to introduce some notation. This is standard notation. Many of you have seen it before. When you have a sum like this, a sum, and in particular, a sum when the index is repeated like this, we can rewrite that, first of all, even if it weren't the index repeated, we could first of all rewrite this as the sum over n, where n goes from 1 to d, from 1 to the total dimension of space, the derivative of phi with respect to xn times dxn. That sum just stands for the sum of these terms. And then, since it happens so many times that you have sums over n of things with repeated indices, and repeated simply means twice in the same expression. It doesn't mean 3 times, it doesn't mean 5 times. If you see a sum with a repeated index, Einstein's summation convention, would I say this was one of the more brilliant things? For anybody else, this probably would have been one of the more brilliant things that they did. Clever things. He was not a man who was known for for that kind of cleverness particularly. But he said, I got tired of writing this over and over. I'm just going to leave out the symbol. This automatically means that you sum over the index n. So divide by the x1 times the x1, and so forth and so on. The sum, adding them up. Whenever you see a thing, let me write another one. Supposing I had an expression b sub n, c sub n, whatever b and c are, I don't know what b and c are, whatever they happen to be, summed on n from n equals 1 to d, we'll simply write that as bn, cn bn, and leave out the summation sign. The only thing we have to be careful about, oh, incidentally, it doesn't matter whether we use n there. N is a summation variable. It's called a dummy index. It's not 1, it's not 2, it's just sum over 1, 2, 3, and 4. We could call it, if we like, exactly the same thing, sum over r, or sum over m. When you're summing over an index, it's just a notation that says sum over it. It doesn't matter what you actually call it. All right, you just mustn't call it something which appears somewhere else in the equation. Give it a name, the summation index, but make sure that it isn't a name that appears someplace else in the equation, because then you get confused. Okay, so that's the summation convention. And the summation convention and the differential change in a field when you move from one point to another. Now, there's another rule. This is the second rule, which we will use over and over. And this is about all we'll use over and over. A second rule, and it has to do with change of coordinates. Change of coordinates, in particular, going from one set of curvilinear coordinates to another, but that doesn't matter right now. We have a set of coordinates, which I've called x. But now let's suppose I use another set of coordinates that I call y. And the y's are different coordinates, so we have some coordinate chart. There's our coordinate chart, or our coordinate map, if you like. But now I'm going to introduce other coordinates. And these other coordinates could be strange curved ones, if I like, or not. There's another set of coordinates, and I'm going to call those y. And the rule, of course, is that if you know what x is, if you know the collection of x's at a point, that determines a point, then there's a definite rule about what the values of y's are. That's what a coordinate transformation is. A rule for going from one set of coordinates, x1 through xn, for a particular point, to another set of coordinates. And so that means that the y's, they also go from, there are also a collection of them, y sub, let's call it n again, y sub n, is some function, let's just call it y sub n, of all of the x's. In other words, if you know all the x's, I can tell you what all of the y's are. If I want y1, some particular function of the x's, which is y1. If I want y2, likewise, and so on. And this, of course, is called a coordinate transformation. Yeah?
Sorry, getting back to the original equation for the infinitesimal movements, do you know what kind of assumptions are being baked in about non-commutation relations or infinitesimal movements with respect to quantum mechanics when you do that?
Oh, let's not get into quantum mechanics now. That's a separate issue. I thought you were going to ask me about second-order quantities.
Well, I was kind of, that was the other part of it. But
yeah. We're assuming all numbers commute, all expressions commute, okay, for sure. As far as second order quantities, this equation is first order in small quantities, all right? And that's what the D means as opposed to delta. Delta would mean an actual finite difference, and then of course it would be more complicated with higher orders in delta. Yeah.
Is there some restrictions on what a coordinate system can be, so that it's actually one value?
Yeah, absolutely, absolutely. Every point has a unique set of coordinates, and every point has a unique set of x1s and through xn's, likewise with the y's, and every set of x's, if I give you an x1 through an xn, that uniquely picks out a point in the space, let's call it P, and likewise, if I give you a point, that uniquely gives me a set of coordinates. That's the assumption of a coordinate frame. And the same should be true for the y's. So that means that there should be a one-to-one correspondence between x's and y's. Was that the question? Oh, for sure, yes. We're certainly going to assume continuity, differentiability, and smoothness of everything. That is, we're going to assume everything is as smooth as you ever need it to be, so that you can differentiate again, and never run into anything singular. So yes, that's another aspect. The x's and the y's are smoothly related to each other, as smooth as we ever need, depending on the circumstances. So that means continuous, differentiable, maybe even differentiable twice, and so forth. Okay, now here's the question. Supposing I know the derivative of phi with respect to all of the x's, xm for all the m's. In other words, I know the set of partial derivatives of phi at a point. We pick a particular point, and supposing I know at that point how phi varies with respect to x's. I want to ask how it varies with respect to y. I would like to compute the derivative of phi with respect to y sub n. And I'm going to write down the answer. If you don't know this, I ask you, please look this up. This is a tool that we will use over and over and over again. It is a kind of chain rule. It's a kind of chain rule. What you do is you first differentiate phi with respect to the x's. And then you differentiate the x's with respect to the y. On the left-hand side, I've picked, let's see what this means with precision, or not with precision, but in very concrete terms. For example, what this would say is pick an n. Let's pick n equals 1. This would say the derivative of phi with respect to y1 is a sum of terms. Note the repeated indices here. So let's write it out explicitly. This means derivative of phi with respect to x1 times the change in x1 with respect to y1. All right. Plus, notice, y1. I've chosen n equals 1 over here, plus the change in phi when I change x2 a little bit times the change in x2. Whoops, x2 when I change y1. Plus dot, dot, dot. Right? The change in phi when I change y1 is given by a sum. The shift in phi when I change x1 times the change in x1 when I change y1, plus the change in phi when I change x2 times the change in x2 when I change y1, and so forth and so on. Dot, 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 up to the last term. All right? That's what this means. I could do the same thing with y2. The change in phi when I change y2 a little bit, we just have to change the index of the y, not the x's. They're summed over, and so on. What's this formula? What's this called? Do you know? Anybody know? I don't know. I don't remember what the name of these rules are. This is a form of chain rule, yes. Okay, so let's write it generally. The change in phi, when you change any component of y, is related to the changes of phi when you change x just by this simple formula. And we can get rid of all of this. And all we have to do is remember the Einstein summation convention. On the right side, m, because it's repeated, is a dummy index. It's not 1, it's not 2, it's summed over. But n, which is not summed over on either side, you get to choose. You can choose n equals 1, you can choose n equals 2, you can choose n equals 3. It's not summed over. And so this is a formula which sort of summarizes all of the derivatives of phi with respect to y in terms of the derivatives of phi with respect to x. All right, let's put these two rules up on the blackboard somewheres, because as I said, they're our fundamental tool for making coordinate transformations. We're interested in coordinate transformations because we want to be able to go from things like curved coordinates to straight coordinates for exactly this reason, that we want to explore how gravity changes when we change our coordinates from curved to straight, or things like that, things of that nature. In fact, in a general space, which is curved, which is itself curved, a space like the surface of a sphere or the surface of a saddle, there is nothing comparable to the rectangular Cartesian coordinates of flat space. We just lay out arbitrary coordinates, and we have to express everything in terms of a set of coordinates which has no preferred special nice straightness in a curved space or curved space-time. And so it's important to learn how to go from one set of coordinates to another, since none of them are particularly preferred. In fact, we're going to want to express the laws of physics in a way which really doesn't depend on the coordinates. But unfortunately, there's no way to write equations without putting some coordinates into them. So we need to explore how you go from one set of coordinates to another. And that's the basic tool of general relativity. All right, so let's put down the two important facts. The change in a variable when you move from one point to another is equal to partial derivative of phi with respect to xm, or x, let's call it xm, dxm, summation convention implied. That's one thing. And the other is that the derivative of phi with respect to, let's call it yn, can be re-expressed as a sum of derivatives of phi with respect to xn m times dxm by dyn. These are our two governing little simple formulas.
Are you assuming the dimensions stay the same?
What's that?
Between x and y, are the dimensions the same?
Yeah. Yeah, I mean, if we need three coordinates to locate a point in three-dimensional space, it's not going to get only 2 coordinates or 6 coordinates if we change coordinate systems. So, right. So the number of coordinates is simply the dimension of the space.
Can you say the second equation is false?
What's that?
Can you say the second equation is false in the first?
It probably does. I'm sure it does. I'm sure it does. Yeah, sure we can. Just change. It does. Indeed it does. Right. But I want to write them both down because we'll be using them regularly. Okay. Now, tensors. What are tensors? Tensors are things which have components, like vectors, and the components change when you go from one set of coordinates to another. Just as a simple example of a coordinate transformation, let's just do something we're familiar with. Let's take a coordinate transformation from coordinates which look like this. rectangular coordinates to another set of coordinates which also is rectangular, just by rotating the coordinates. As an example, here's another set of coordinates superimposed on top of the first. And the red ones we can call y, the black ones we can call x. And now let's take a vector. Oh, do I have another color? Let's see if I have another color. Let's take a vector. There's a particular vector. And that is that color visible? Yeah, everybody fine with purple? Okay. That's some specific vector. All right? It has components. Its components we just get in rectangular coordinates. We just get its components by dropping perpendiculars to the axes. And the two components, the x component and the y component. If it's sticking out of the blackboard, there's also a z component. But we simply drop perpendiculars from the tip of the vector down to the coordinate axes, and that defines the components in a familiar way. And of course, the components depend on which coordinates we're using. The coordinates of this vector in the y frame of reference is gotten again by dropping perpendiculars to the axes, but they're different axes. So the components of a vector do depend, in general, they depend curvilinear or not curvilinear. They do depend on the coordinate frame. And there are rules that you can work out easily, we're going to talk about them, for relating the coordinates of a vector in one frame of reference to the coordinates in another frame of reference. If we have some vector equation, an equation that some vector is equal to some other vector, then the only way to express it with equations is to express it in terms of components, but we want to make sure that it's an equation which is true in all reference frames. And so we have to know how to go back and forth components of things. All right, so a vector is one thing which has components. And how many components does a vector have? Again, in a d-dimensional space, you can think d equals 3 if you like, but in a d-dimensional space, the number of components that a vector has is d. A vector is a special case of a tensor. It's a tensor with only one index, or a tensor of rank 1. All right? A simpler thing, which is also a tensor, but which is even simpler, is a scalar. A scalar is a quantity which really doesn't have components. It doesn't have a sense of directionality. It's just a number, a numerical value. It doesn't have any components. When I write down the scalar phi, let's suppose that phi is a scalar. It doesn't have to be in that equation. But let's suppose that phi is a scalar. Then that scalar has a numerical value at every point. And that, like, for example, the temperature. The temperature in space doesn't depend on whether I choose coordinates one way or the other. It's a scalar. But it's a special case of a tensor, and it's a tensor with no indices. It has no indices at all. It's a tensor of rank 0. A vector is a tensor of rank 1. We're going to explore quantities which are tensors with any number of indices. And these things are more obscure. They're harder to understand geometrically, but eventually you'll get familiar with them. And the rules for them we can work out by starting, the best place to start is with scalars. Let's start with scalars and talk about how they transform from frame of reference to frame of reference. Well, the answer is they don't. They stay the same. So we could write that in the following, with the following notation. The field phi, in conventions in which we use coordinates y to describe it, let's call it phi of y, is equal to phi of x if x and y here label the same point. This is the expression for phi in the x coordinates. These are the x coordinates. Here's the y coordinates laid down. I'm going to draw them over here. There's the y coordinates. And let's suppose that this point and this point really are the same point. Then there's only one value of phi. It's the value of phi at that point. And the transformation property of a scalar is trivial. Nothing happens to it. The temperature at a point of space doesn't depend on which way the coordinate axes, or even if you're using curved coordinates. And so this is the transformation property of a scalar. Okay. Now let's come to a vector. How do the components of a vector transform when you go from one frame of reference to another? We need to start with some vector. We need some quantity which is a vector. And a simple vector, perhaps in many respects the simplest vector, the primordial vector in a sense, is a little displacement. A little displacement, namely the thing that we already called d phi, dx, excuse me. Dx represents a vector, and we can put an arrow on top of it to indicate that it's a vector. It's nice to indicate vectors by arrows. And it simply means a little differential displacement. It's a sort of quintessential vector, a little small displacement. Okay? Now, it has components. This stands for the vector itself. The vector itself is a geometric object. It has components. The components of it are just dx1, dx2, dx3, and so forth. In other words, the components of it are just the little displacements in the x-coordinate frame. So again, if this is the x-coordinate frame, and this is dx, then these dx's are just the little displacements of the coordinates themselves. All right? That same vector can be described in y coordinates. The same physical vector, think of the vector as a little stick with a pointer on it. That same physical vector has components in the y coordinate frame. And the question is, how do we find them? Those components are, starting at this point and ending at this point, the components are dy1. I've written it as if it were three-dimensional space, but as many as you like. It's the same vector, but with the components being expressed relative to two different coordinate systems. What's the relationship between them? Well, let's suppose we go from one point to another, and let me focus. Remember, these y's here are all functions of x, and the x's are also functions of the y's. They're functions of each other. The x's and y's are functions of each other. Let's concentrate on dy1 over here. What's the change in y1 when I change x by a little bit? For that, I use the top equation, except phi now being replaced by y1. The change in y1, now we're just going to repeat that equation, is the derivative of y1 with respect to xm dxm. You get it? The change in y1, I'm just using that exact formula up on the top, except with phi being y1. The change in y1, when I move in x space a little bit, is just the derivative of y with respect to x times the change in x, summed over m. What if I were changing y2? Well, what would be the change in y2 when I go from one point to another? I just replace, put 2 up here. What if I pick a generic index n? Then it just becomes the differential displacement in yn is just the derivative of yn with respect to xm times dxm. All right? Well, this tells me explicitly how the components of the small vector transform. They transform by getting multiplied by this collection of things dy by dx. Now I can tell you what the definition of a contravariant vector is. The definition of a contravariant vector is a collection of things which have components in both the x frame of reference and also components in the y frame of reference. And those components, let's now be general. Let's call it V. V for vector. The components of the vector v1 through vn in the y frame of reference. Let me put down here in brackets that these are the components relative to the y frame of reference. In other words, relative to the y coordinate system, are equal to the derivatives of yn with respect to xm times vm in the x coordinate frame. In other words, they behave exactly the same way as these little differential vector components of a little displacement behave. Now, don't ask me why this is true. This is definition. This is definition of an object which transforms contravariantly. It's just a word. It doesn't, for our purposes, it doesn't mean anything right now. That's the definition of a vector, or a contravariant vector, that its components, whatever they are, that they transform when you go from one frame of reference to another through this collection of quantities, dx, dyn by dxm. How many quantities like there are there altogether? How many? D squared. D squared. Right. Any y can be differentiated with respect to any x. Yes. And so there are d squared such coefficient functions here. And this is the way you transform a vector. To those who are familiar with linear algebra, this is, of course, a matrix. And this is a column vector, and here's a column vector, but we don't need that right now. This is the transformation property of a contravariant vector.
Does contravariant refer to the nature of the coordinate system? Or?
No, it refers to the way it transforms. The way it transforms, that's right. The way it transforms. We're going to discover other objects called covariant tensors. But so far, this is just a mere vector, something that's pretty easy to visualize. Now, a tensor of rank 2 is an object which is not so easy to visualize. You should think of it somehow as having two directions, so that's a thing that has built into it two directions instead of one. But there's an easy way to think about the simplest tensor that's made up, the simplest tensor of rank 2 can be simply thought of as a product of two vectors. Given two vectors, and they could be the same vector or they could be different vectors, it doesn't matter. Let's call one of them A, and it has components m, a sub a m. And now let's take another vector, which we'll call B, and write its components down. How many such things are there altogether? I can multiply. There's a whole collection of objects I can make up. I can take any one of the components of A and multiply it by any one of the components of B, and that's an object. It's an object that may or may not be interesting. We're going to discover ones which are interesting. How many such components does such an object have? This has d components. This has d components. The number of components altogether is d squared. So this is an object which has d squared components, and the individual components are labeled with two directions. This is a special case of a tensor of rank 2. It has two components, it has two indices, and altogether d squared individual components. How does it transform when I change coordinate systems? Well, this is easy. I already know how the vectors transform. So all I need to do is, let's work it out. Let's work it out. Let's take let's compute an, am, bn in the y frame of reference. In other words, where the coordinates are written relative to the y frame of reference. Well, here's a rule for connecting components of a vector in the y frame with components of the same vector in the x frame. So let's just apply it. Let's relate these. Now, first of all, there's A. A is a vector are not dummy indices. They're picked. This could be 3, this could be 2, but they're not summed over. Dummy index is one which is summed over. All right, so here's the matching. This index matches this index, so we better put an M up here. And then we differentiate it with respect to a dummy index. I don't want to call a dummy index N now, so I'll call it XR times AR. That's just this piece of it over here. AM of y, this should be of x. AM in the y frame of reference is the derivative of ym with respect to xr times ar summed over r. Now that's only half the expression. The other half involves what happens to b. So let's write that down. Again, we should match indices. Here we have the nth index, so that means some derivative of y n. Now I need another dummy index. I need another dummy index. I've already summed over r. I can't call it r again, so I'll call it s. xs times dx times a times b s in the x reference frame. All I've done is taken a and b and separately transformed them from the x coordinates to the y coordinates. But now let me just regroup it. Let me just regroup it by taking this over here and writing ARX. AM times BN is called TMN, a tensor of rank 2 with index m and n. So I can call this then TMN with components in the y frame of reference. That's equal to dym by dxr, dyn by dxs. And what shall I call this? It's also some t. It's also the components of a tensor built up out of a times b. Okay? Not TMN, but TRS. TRS. The first entry has to do with A, the second entry has to do with B, so I should really invert the order of them. B, S, X, just to make it look the same as on this side. And then what do we see on the right-hand side? On the right-hand side, we have TRS evaluated, or its components in the X frame of reference. So this little operation has defined for me a new class of things which are tensors of rank 2, which transform in this manner. Notice it's very similar, except sort of doubled. Each time you want to transform an index, you get a factor dy by dx. For each index, here's the index m. You have a dym by dxr, and this is a dummy index. And then for the n, you have a dyn by dxs. And then it multiplies the t with the rs index in the other frame of reference. This is a pattern. You could do the same thing for tensors with any number of indices up here. I'll leave it to you to work out the rules. They're easy. They're just simple generalizations of this, where for every index you get another factor like this and another index up in the tensor over here. That's all a tensor is. That's the whole definition of a tensor. These tensors are generally functions of position. They're functions of position in general, just like vectors can be vector fields and vary from place to place. But this is the rule for transforming tensors, and that's all there is to it. There's no other definition of a tensor than this. And we're going to see some examples of them. Rather than try to give you a deep geometric insight into them, I think we'll work with them for a while, get familiar with the machinery for them, but we're going to see some examples of them. Okay, so that's the definition of a tensor with contravariant components. We're going to come to what a covariant tensor is, and you'll understand the difference, but all of these indices are transforming the same way. They're transforming with coefficients dy by dx. Not dx by dy, but dy by dx. When you want a thing in the y frame on the left-hand side, then it's dy by dx on the right-hand side times tx. All right, that's the definition of tensors with all contravariant indices. Next, let's see, should we take a break or should we take a break in another 10 minutes?
I actually have a question on this. When you make those rearrangements, right, you've made a lot of assumptions about the math behind this, right, the tensors, right? Well, I mean, you're assuming they're commutative, and it's not a cross product, not a dot product.
Yeah, no, these are just numerical multiplications.
Okay,
yeah. There's nothing. You can invert the order of anything times anything else as long as you're just multiplying numbers. And each expression on the blackboard is a number.
I think there are some assumptions in there. The matrices should be invertible, right?
You mean these are matrices, and they are invertible. The assumption that they're invertible is equivalent to the statement that there's one-to-one mapping from x to y and from y to x, that you can invert the coordinate.
And the other thing is that you have your first rule is basically a total differential, and that means that it has to be exact.
Yeah, that just means it's a function. It means it has a value everywhere, well-defined value everywhere, that's all.
Well,
no.
It means that the partials have to have good quality.
No. Well, assuming everything is differentiable, that's all you have to assume.
Twice differentiable.
Twice differentiable.
And they can mix.
And what?
You can switch the order.
Then you can switch the order of differentiation.
Then you're good.
Yeah. Right. Right. All right, let's spend a few more minutes and spend a few more minutes with the idea of a covariant vector. The top thing, d phi, is the archetype of a contravariant vector. d phi, or sorry, dx. dx is the archetype of a contravariant vector. It has components, and its components are simply this. Here's another object with components. How many components does it have? It's the collection of partial derivatives of phi. It also has d components, has the same number of components as dx here. It's also an object that one could call a vector insofar as it has components, but it's a geometrically different kind of thing. It's not a displacement, but it's the gradient of a function. It's the rate of change of a function along different directions. An object like this is called a covariant vector. More precisely, they're called the covariant components of a covariant vector. Covariant components of a vector. But we can also ask, given a collection of objects, d phi by dxn, here they are, d phi by dxm, here's a collection in the x frame of reference, how do they transform? In other words, if I gave you this covariant vector, namely d phi by dx, the collection of components, how do I calculate d phi by dy? Well, here's the rule. Here's the rule right here. I don't need to go any further. And I can abstract from this rule a more general idea of a covariant vector. Instead of taking d phi by dxm, let's just define an object to be a covariant vector if it transforms in the following way. I guess I can use the same letters. I'll use the same letters, but now we're talking.
The other one except upside down.
What's that?
It's kind of the same thing as the
Yes. We're going to compare the two in a minute. All right, so here is A. I'm going to put its index downstairs. Why? Just because it looks nice. This is down lower than, but there's a real reason. There's a real point. There's a real point. We'll come to it in a moment. But when you write covariant indices, you always write them downstairs. When you write contravariant indices, you always write them upstairs. The difference between the covariant and the contravariant are how things transform. So here's an example of a covariant object, which it's just a definition now that we put the index downstairs. It turns out to be a nice definition, a nice notation. It's a notation. It's not a definition. A sub n in the y frame of reference, its components in the y frame of reference, are equal to dxm by dyn times a sub m in the x frame of reference. These are the components in the y frame. These are the components in the x frame. d phi by dx is the component of a in the x frame, d phi by dy in the y frame. Okay. All I've done is abstract out of this, replace d phi by dy by a, and d phi by dx also by a. And this now defines a class of objects which may be more general than just gradients. Any object whose transformation property is like this is called a covariant vector. Now let's just look at the difference between the transformation properties of covariant and contravariant vectors. I'll use this as my typical contravariant vector. And now let's write the corresponding thing for the covariant vector. an in the y frame of reference is now equal to dx by dyn m, or let's call it r, I guess I can call it m, times a m in the x frame of reference. Notice the difference. One of them involves the set of derivatives dy by dx. The other involves the set of derivatives dx by dy. Notice that there's a very nice pattern here. The index upstairs is upstairs on both sides of the equation. And when you contract, or when you sum over indices using the Einstein summation convention, it's always an upper index with a lower index. That's a general rule, that when you sum over indices, you should be summing over indices one upstairs and one downstairs. There's something wrong with your equations if you're identifying indices and summing with both of them either upstairs or downstairs. But thus far, it's just a notational device. And we see it has that pattern that a thing which is downstairs on the left is also downstairs on the right. And when we sum over a dummy index, it's always an upper one with a lower one, which is a sort of cancellation. An upper one cancels a lower one and gets rid of it, so to speak. That's the pattern. There's no theorem here. It's just an observation about these equations. And these are the two transformation properties. And once I have the idea about how a covariant vector transforms, I can define objects which have several covariant indices. Covariant indices mean indices downstairs. And I'll give you an example. Same deal. Exactly the same deal. I go through the same thing except with covariant indices. And let's see if we can figure out or guess what the transformation properties of a tensor with two covariant indices is. All right, so now it's two covariant indices. This is the y frame of reference. We have to turn the derivatives upside down. They become dx by dy instead of dy by dx. And on the right-hand side, we also should have lower indices, rs, x. We have a tensor with two downstairs. You know, incidentally, I don't believe I've ever in my life heard a physicist actually refer to covariant indices and contravariant indices. We just call them upstairs and downstairs, because nobody can ever remember which is which. I looked it up tonight so that I get it right, but every time I do, I forget the next time. Incidentally, what do I have here? Let's put the indices in. There's lower indices here. Better mean there are upper indices here if we're going to sum over them. And there's lower indices here, so there better be an m and an n.
It's R and S.
R and S.
Oh, R and S. Thank you.
You know what I think it is?
Yeah.
I think partial derivatives are in some sense like basis vectors.
They are.
And so varying like the basis vectors is covariant.
Mm-hmm.
That's where that terminology comes from.
Perhaps. Where the contra came from, I don't know. But you can check the pattern of these things. There's always a pattern to them. When you sum over indices, it's an upstairs with a downstairs, upstairs with downstairs. The left-hand side here has downstairs indices, m and n, and so it's not too hard to keep track of. And by inspection, you can see whether your equations make good sense in this respect. Okay, let's take a break, and then we'll come to the metric tensor. The metric tensor itself, the metric tensor is a tensor, and it's an important one. Okay, let's get started. I think I'm going slowly. I hope I'm going slowly. I'm going intentionally slowly, which means I'm telling you things that many of you already know, but I'm going at a rate which I'm hoping will carry along the majority of you. We now want to come to the idea of a metric tensor. Let's begin with ordinary conventional, I will call it by its right name, flat space. Incidentally, let's distinguish two things. There is flat space, which I have not defined for you yet, but the tabletop here is a flat space. The blackboard is a flat space. The surface of a sphere is not a flat space. And there are flat coordinates. Flat coordinates usually are taken to mean, when people speak about flat coordinates, it's usually, it's an abuse of language. But what they mean is rectilinear, pretty much Cartesian coordinates, sometimes spoken of as flat coordinates. The axes are not curved, the axes are flat, and so forth. So we can speak of flat coordinates, and we can speak of flat spacetimes, or flat spaces for the moment. All we're doing is space now, not space-time. Quite a distinct concept. You can introduce, as we will do it, we can introduce, for the discussion of flat space, there's nothing to prevent us from using curvilinear coordinates on it. On the other hand, there's no clear concept of flat coordinates on curved space. Curved space, you can coordinatize it, you can lay down coordinates on it, but there's no sense in which one set of coordinates is any straighter than the other set of coordinates. And so I thought I would just point that out to you. In a curved space, It's basically a space which has an obstruction in it, a mathematical obstruction, to using flat coordinates. This word obstruction I'm using over and over again, and I do want you to think of it as being related to the obstruction in removing a gravitational field by changing coordinates. Here in geometry, it's a question of whether, well, let's write down what the metric is first, and then I'll tell you exactly what it's an obstruction to, what curvature is an obstruction to. Does everybody know what I mean by the word obstruction? I mean a mathematical property that forbids you from doing something to simplify a situation in a certain way. Okay, let's start with flat space. I'll draw it, of course, as two-dimensional, and I will introduce some coordinates. And I'm going to take the simplest set of coordinates, Cartesian coordinates. It is not important for us whether they're tilted this way or that way. We can rotate the coordinates. But let's take an infinitesimal vector dx and think of the length of the vector. All right, I'm going to take the square of the length of the vector. In 2 dimensions, we can just drop perpendiculars and rewrite the length of the vector in terms of the components. This is, of course, also true in higher dimensions, 3, 4, 5 dimensions. And we use the Pythagorean theorem. Let's call the length of the vector, let's call it ds. It's also small, so it's also differential. And the Pythagorean theorem for 2 dimensions here would say that the square, it's just the square of the hypotenuse, we'll call it ds squared, is equal, in this case, to dx1 squared plus dx2 squared. Now please, let's not confuse notation. These superscripts over here are labeling which coordinate we're talking about. This superscript over here literally means square. dx2 here does not mean anything squared. It just means the second coordinate. This means the first coordinate. So I'm putting them in brackets just so you'll know. If I didn't put them in brackets, you would think it was dx12 or dx22. So I put them in brackets. That's the Pythagorean theorem. If there were more coordinates in a higher dimensional space, and we were using Cartesian coordinates, we would write dx3 squared here and so forth. Okay, let me write this in another way for you, which is sort of slightly contrived. I don't know, maybe it's not so contrived. First of all, I can write it in this fashion. dxm dxm. Now, this is violating one of my rules about repeated indices. My rule about repeated indices is that you should put one upstairs and one downstairs. Okay? So I am explicitly violating that rule, but in order to, I'll just remind myself that it really means sum over m. And this means dx1 squared plus dx2 squared plus dx3 squared. And as I said, I've explicitly violated a rule which I set out, but I want to restore that rule. I want to rewrite the same equation in a way which restores the rule. And so I'm going to invent a new symbol. What's the new symbol? Anybody know what it is? Eta. Not eta. Chronica, delta. Right. 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 Eta is the other symbol that I could have, but the mathematical symbol delta mn. That mathematical symbol has the following meaning. It is, how many components does it have altogether? D squared. Each m and each n, it has a value. Its value is equal to, its numerical value is equal to 1 if and only if, IFF means if and only if, m is equal to n. In other words, delta 1, 1, delta 2, 2, delta 3, 3 are all equal to 1. And it's equal to 0 if and only if m is not equal to n. So that means delta 1, 1 is equal to 1. Delta 2, 2 is equal to 1. Delta 3, 3 is equal to 1. Delta 1, 2 is equal to 0. Delta 1, 3 is equal to 0. Delta 3, 2 is equal to 0. That's the meaning of the symbol, mathematical symbol. And, you know, it's partly some interesting mathematics and partly simply notation, a notational device to be used to simplify equations. All right, now, I can rewrite this in the following form. Notice I've put these indices downstairs. All right. I'm going to rewrite this as equal to delta mn, with two downstairs indices, dxm dxn with two upstairs indices. Let's see what this thing means. It means, and m and n are both summation indices now. They're both summation indices, one upstairs and one downstairs, one downstairs, one upstairs, one downstairs, one upstairs. So this now conforms to my rule about the way that you combine indices together. If you want to sum over a repeated index, make sure one is upstairs and one is downstairs. Now, what does this give you? Well, every time m is equal to n, delta mn is 1. So that gives you things like delta dx1 squared plus dx2 squared plus dx3 squared and so forth. In other words, when m is equal to n, you get a dx squared, and you get one for each numerical value of m. Okay? What about when m is not equal to n? Are there any terms in here with dx1 times dx2? No, because delta 1, 2 is equal to 0. So this expression here, that's the purpose of delta mn, is to pick out the contributions when this m is equal to this n, and that means just summing the squares of the dx's. That's what a delta mn, and it simply restores the rule. Writing it in this way restores the rule that, when you use the summation convention, you should always be summing over one upper and one lower index. All right, so here's a neat form for ds squared. Delta mn dxm dxn. But now I want to write this. I want to write the length of this vector not in x coordinates, excuse me, not in x coordinates, but in y coordinates. The same little vector, the same precise little vector, which has exactly the same length, but I want to write it now in terms of the differential displacements in some other coordinates. In particular, I have in mind curvilinear coordinates of some kind. So let's rewrite the same expression. What we need is a formula. Let's erase the blackboard here. We need a formula for dxm, for example, this one over here, in terms of dy's. If I had that, I could plug it into here and re-express this in terms of the dy's. So what do we know about dxm? For that, we use the top formula up on top. Let's see. Except with x's being replacing y's. All right, I'm going to write the formula. I think you'll all recognize it. The change in xm, when I move from one point to another, is equal to the derivative of xm with respect to yr dyr. This is an application of the rule up on top, except where there are y's here instead of x's, and where the thing which is changing, d phi, is just xm. Same rule, a change in a certain quantity is the derivative of the quantity with respect to y times the change in y summed over the components. All right, so that's all we need to do now. We can now rewrite this distance in y notation. Let's do it. Here it is, ds squared is equal, all right, let's see what we have. Delta mn, that's this. Now we have dxm, that's this. Partial of xm with respect to yr times dyr, but I'll write the dyr in a moment. I don't want to write it down yet. Yeah, let's put it over here, dyr. But now we also have to put in dxn. So that's going to be partial of xn with respect to ys times dys. Now look what I have. I have an expression for ds squared that involves some complicated collection of functions. First of all, m and n are dummy indices. They're summed over. The things which really this depends on are r and s. The right-hand side doesn't depend on m and n. They're summed over, but it does depend on r and s. So let's give this a name, this quantity, this whole quantity here. It has a value for each r and each s. But it's summed over in m and n. I'm going to give it the name GRS. Notice that it has lower indices below the fraction bar here. GRS. It's a function of position in general. Let's call it of y. It doesn't matter whether we call it as a function of x or y, since if we know something as a function of x, we automatically know it as a function of y. But I want to be working in y notation. So I call this GRS of y, and in general it depends on y. It's not just a collection of numbers, these are a collection of functions. GRS of y times dy s dyr. What's the lesson? Of course, this is a special case, or this is similar. It also contains dx's times dx's, but it contains the Kronecker delta. Here we have a very similar thing, except instead of the Kronecker delta, we have a collection of, again, d squared coefficients. For each r and each s, there's a g. It's no longer true that the g11s are equal to 1 and the g22s are equal to 1. They're not. They're all whatever they are. Nor is it true that g12 is equal to 0. This is called the metric tensor. This is the metric tensor. And it's a thing with two lower indices, two covariant indices, and it's actually easy to prove. It's quite easy to prove that it transforms. In fact, I'll prove it in a moment now. It's easy to prove that it actually transforms as a covariant tensor. How can we do that? I started in this case here with something I knew very well, just Pythagoras' theorem in Cartesian coordinates. That led me to introduce, let's call it now, the metric tensor in Cartesian coordinates. This is the metric tensor in Cartesian coordinates. I just read it off from Pythagoras' theorem. And then I changed coordinates to another set of coordinates and found out that the only thing that happens is the delta mn is replaced by a g, which depends in general on position. Okay. Incidentally, for this case, where I started with the blackboard, flat blackboard, when I say blackboard, when I started with a flat space, we know, although it might not be obvious from this form, I might give you some form like this, whether it's obvious or not, we know that we can always transform it back to this form that looks like Cartesian coordinates. We'll come back to that in a minute. But what about the general transformation properties of this thing which I'm calling a covariant tensor? How can we work them out? Well, here's the way. Let's start with a general expression among the x components. Let's not assume that the space that we're talking about is either flat or that the coordinates are Cartesian. All right? That means that we should start with a more general expression here in which this is Gmn of x. In other words, we should make it look more or less like it looks on this side over here in our starting form. Let's suppose we did that. Then ds squared would be given by this general form over here, but on this side, we would just replace the delta mn by Gmn of x. What have I shown? I've shown that the GRS in y notation, the y components, are given by the x components times the standard dx by dy coefficients. This is exactly the transformation property of a covariant tensor of rank 2. So the metric tensor is a covariant tensor of rank 2. If I give you a general space, I mean it could be curved, it could have geometric properties which are not the geometric properties of a flat plane. It could be the surface of a sphere, surface of a saddle. We can always write the metric tensor, or the distance between neighboring points, can always be written in this form. The question is, under what circumstances can we find a coordinate transformation from y to x so that this can be brought back to the form delta mn? In other words, is there some, if I were to have given you the y coordinates, and I would have given you the description of the distance between every neighboring point in this form here, that's equivalent to telling you what the geometry is like, if you know the distance between every pair of neighboring points. If I were to give you GRS of y, and I gave you this general form, I can ask the question, is there some does there exist a coordinate transformation which will bring it back to this form which looks like Cartesian coordinates and flat blackboard in 2 dimensions or in 3 dimensions? If the answer is yes, in other words, that this complicated GRS of y can be undone by coordinate transformation and brought to the form of Cartesian coordinates in flat space, then the space is called flat. It means that you may have chosen complicated curvilinear coordinates, but there's no obstruction to straightening out those coordinates and writing it in the form of flat space. That's the definition of a flat space, a flat Riemannian space. The term is Riemannian, refers to this kind of geometry, that there exists a coordinate transformation that will flatten out the metric and turn it just into this collection of zeros and ones. In other words, that it will restore the standard flat space form of the relationship between points, neighboring points. If not, that means there is no way, there is no coordinate transformation which will undo and get rid of the spatial variation, the complexity of this, the fact that this varies from space to space and so on, that point, will not bring you back to this, cannot get back to that. The space is called curved. Curvature, in that sense, is an obstruction to removing the curvilinearity of the coordinates, if you like. Or in that sense, yeah.
So I think I understand. Sorry if I'm understanding. If you have a coordinate system that's not Cartesian,
right,
but you can convert it into this Pointer delta.
Then it is flat. Then it's flat.
Okay.
Right.
If you cannot, then it's.
That's right. If you can't, then it's called curved. Now, it's possible that a space be flat in some spaces, in some places, and not in others. For example, this tabletop could be connected to something over here which was a spherical dome or something. In that case, what is true is over some region of space, you can find a coordinate transformation which will straighten out the metric, but not everywhere. So, you know, a space can be locally flat, so it can be flat in some region, but that doesn't mean it's flat.
It can always be flattened at any one point.
Oh, it can always be flattened in a vicinity, in a differential, infinitesimally small vicinity of a point. Yes, that's right. But that of course is true. But I mean, sometimes it can happen that the space might even be flat over some extended region. For example, just take this table, put a lump in it, a bump in it over here, and the lump comes up and goes over like that. It has some regions of negative curvature and positive curvature, and those curvatures cannot be gotten rid of. But still, over here, you could still fix up the metric so that it looks flat. All right, that's the basic idea of a metric tensor, and it is the key thing, the key object of Riemannian geometry. The subject we're doing is Riemannian geometry. Yeah?
Can you have a space that's flat except for one point?
Yes, yes, you can. Yes, that's right. The tip of a cone, that's right. A cone is a space which cannot be flattened, but you can flatten out any patch of it. All right, so here's our cone. That's a good point. Here's our cone. And if I slice the cone like that and open it up, I make a thing which looks like this. It can be flattened onto the blackboard, and then if I take my coordinates in the blackboard to be good old Cartesian coordinates, that lays out some coordinates on here which are flat. But it's always going to fail at the tip. So yes, so the tip of the cone is an obstruction to finding global flat coordinates. I use the term flat coordinates, which is an abusive terminology. Flat coordinates, I mean coordinates with this property. All right, let's, is this clear? Yeah, okay. Let me just do a couple of examples of metric tensors of spaces. Just the first example is an example which is really just flat space. It's flat space in curvilinear coordinates. We've talked about it abstractly. Let's do it concretely. A specific example of coordinates that we use all the time in which the lines of constant coordinate, you know, the coordinate axes, whatever you want to call them, are not straight lines. Polar coordinates. Polar coordinates in 2 dimensions, polar coordinates in any number of dimensions, but in particular polar coordinates in 2 dimensions are examples of curvilinear coordinates in a flat space-time. Flat space. We have not gotten to space-time. Flat space. All right, let's just do it. We can work this out easily. So here we have x and y. Now I'm talking about 2 dimensions, but in these formulas, there's nothing specifically 2-dimensional about it. You may not be able to visualize a higher dimensional curved space. I can't. But you can push the symbols around, and it doesn't really matter whether m and n go from 1 to 2 or whether they go from 1 to 10. You do exactly the same manipulations. But now I am dealing with a 2-dimensional space that you can visualize. So there's x and y, and I'm going to replace them by the polar coordinates, r meaning radial distance and theta meaning angle. So here's a point, and it's at a distance r from the origin at an angle theta. What we need to know is the relationship between x and y, well, x and r and theta, and y and r and theta. All right, now that's easy. We just drop a perpendicular here, and x, the x location of this point, is equal to r times cosine of theta, and y is equal to r times sine of theta. Cosine of theta is Adjacent over hypotenuse, and sine of theta is opposite over hypotenuse, and that's what these things say. Now, I want to write the metric, which we know what it is. It's just dx squared. Let's write it over here. It's dx squared plus dy squared. Oh, incidentally, my use of x and y here is not for two different coordinate systems now. I should probably call it x1 and x2 to be consistent. But when I'm dealing with a two-dimensional blackboard, sometimes I will just call it x and y, and forget this over here. The x squared plus the y squared, which really I should call the x1 squared plus the x2 squared, the x squared plus the y squared is equal to ds squared, right? That's good old Pythagoras. But now all we have to do in order to rewrite the metric in terms of r and theta is to express dx and dy in terms of dr and d theta. So let's do that. Let's differentiate this. Dx is equal to the partial derivative of this with respect to r, that's cosine theta, times dr, partial of x with respect to r times dr, plus partial of x with respect to theta. What's the partial of x with respect to theta? It's minus r times sine theta, right? When I differentiate cosine, I get minus the sine. So that's minus r times sine theta. Okay, that's dx. And what about dy? Sorry, times d theta. And what about dy? Same kind of thing. The only difference is now, well, this piece is similar. Sine of theta dr. Now it's plus r cosine theta d theta. And now I just want to write dx squared plus dy squared. That's a whole bunch of terms, but they're not very complicated. Let's see what we have. When I square dx squared, I'm going to get things involving dr squared. I'm going to get things involving d theta squared. And I'm going to get things involving dr times d theta. All right. Let's look at the dr squared terms. You get one from here, cosine squared times dr squared, and you get one from here, which is sine squared dr squared. When I add them up, cosine squared plus sine squared is 1. And so I'm first of all going to get that this is equal to, the first contribution will just be dr squared. That's easy. And it's just gotten by squaring this term and adding them together. Then there's going to be another term which comes with d theta squared. It'll also have this squared plus this squared. So it's going to have r squared sine squared theta, and it's going to have r squared cosine squared theta. The minus sign will go away when you square, so it's just going to be r squared d theta squared. The sine squared plus the cosine squared, again, add to 1. This is plus r squared d theta squared. And what about the cross term, the dr d theta term? Let's look at it. From here, squaring this, you'll get a cosine theta, sine theta, r with a minus sign. Get r cosine theta, sine theta with a minus sign. From this cross term, you'll get plus r cosine theta, sine theta, and there will be no cross term. All right, so this is the metric of flat space in polar coordinates. Let's write down the components of the metric. The components of the metric are not now just zeros and ones. The coefficient here is 1, but the coefficient here is more complicated. It depends on position, depends on radius. So, first of all, what's GRR? I use the index r here to represent the r coordinate. I'll use GRR and G theta theta instead of G1 and G2, instead of 1 and 2. What's GRR? 1. Why is it 1? It's just the coefficient of dr squared. What about GR theta? That's the thing which would multiply dr times d theta, and that's 0. There is none. So that's 0. So far, it looks exactly the same as flat space, but the new thing comes when I write g theta theta. And that's not 1, it's r squared. So that's the metric of space-time. Sorry, I keep saying space-time. That's the metric of two-dimensional flat space in polar coordinates. Now, if somebody gave you this metric and you looked at it, you say, oh, this is kind of complicated. The g theta theta term varies with distance. Is this flat space or isn't it flat space? Can I find a coordinate transformation which will straighten it out so it just becomes dx squared plus dy squared? Well, in this case, of course, we know the answer is yes. And it's just this coordinate transformation. If I gave you this metric, these set of components, and I undid, in other words, I go in the opposite direction and work out the metric in terms of x and y, I find that it's dx squared plus dy squared. So that is a flat space by definition. There are a set of coordinates. There is a set of coordinates. More than one. Of course, you can tilt the coordinates and rotate them and translate them and do all kinds of things. But there's at least one coordinate system where the metric just looks like the Kronecker delta. So that's flat, despite the fact that in this form, things have a nonlinear complicated dependence on the radial distance.
Right.
Yeah.
Does the off-diagonal term being 0 tell you anything about the space?
Yes, it doesn't tell you anything about the space in this case. It tells you something about the choice of coordinates. I'll tell you, no, good, I meant to come to that right now. Let me tell you exactly what it tells you. It tells you, all right, let's look at the lines of constant r and the lines of constant theta. The lines of constant r are circles. The lines of constant theta are straight lines from the origin. The fact that there's no cross term is an indication that the lines of constant r and the lines of constant theta are perpendicular to each other. That's also, of course, true for the lines of constant x and y. They're perpendicular to each other. But that's the meaning of the cross term vanishing, that the r and theta, or that the axes, the lines of constant coordinate, or you can think of them as the axes, are perpendicular to each other. That I have not changed by doing polar coordinates. I could have used some more complicated coordinates, for example, ones which look like this. That's an interesting exercise. Find some coordinates where these lines are not perpendicular, and then you would have had a gr theta. Okay, so there was nothing particularly special about the fact that this vanished, other than my particular choice of metric happened to have this perpendicularity aspect to it. All right, let me give you the metric for a sphere, and I will allow you to prove that you cannot straighten out the sphere, that you cannot find coordinates in which the sphere is flat. This is a unit sphere of radius 1. That doesn't matter very much. That's got nothing to do with it. I've just chosen the sphere to have radius 1. All right, so here are my coordinates. Now, I could use many different sets of coordinates on the sphere. It doesn't matter which set of coordinates I use. I won't be able to straighten out the coordinate system, but I'm going to give you one set. And the one set is basically good old longitude and latitude, except I always measure longitude from the South Pole. In other words, no, I measure latitude from the latitude from the South Pole, right? Longitude, and then it goes east-west, right? This is another thing I can never remember. Longitude is east-west. Latitude is north-south. And just because I'm used to it, I always choose the latitude, yes, the latitude to be 0 at the South Pole. All right, so you pick a point on the sphere. Doesn't have to be on the great circle, and you locate it by a polar angle. The polar angle is one word for it, or latitude, which I'll call phi, and also a longitude, which I'll call theta. those are two coordinates, good set of coordinates for a sphere. The lines of constant theta and the lines of constant phi are perpendicular, so I still have a case where I'm not going to have a cross term. And now you can take any small vector or any small interval. The small interval is characterized by a d theta and a d phi, and you can write down the distance from one point to another using Pythagoras' theorem on the sphere, and I'll write down the answer for you. It's just d phi squared. As I said, this is radius r equal 1. It's d phi squared plus sine of theta, sine of phi squared, sine of phi squared d theta squared.